Welcome back and thank you for joining. We'll continue with some examples of applications of multiple transformations on the graphs of parent polynomial functions. Now remember that whenever a polynomial function of the form y equals f of x is transformed, so pretend y equals f of x is a parent function, then its equation is changed to become y equals, so we're still going to have the parent function sitting here, f of x, but now we will see a coefficient a that will multiply f of x, so that will change the y values in the y direction. It's a multiplier. That means that it will either expand it or compress it vertically. A coefficient k, that's the coefficient that multiplies x, which means that it will change the x values of the function. So it will change the graph of the function in the x direction by either compressing it when k is bigger than 1 or expanding it if k is less than 1 in the horizontal direction again, and then minus a number d that is subtracted directly from x, so it will change the function in the horizontal or in the x direction by simply translating it because it's a number added or subtracted. And lastly, we will have a coefficient c. This is a number that is added to the entire function. When c is positive, the function will be moving up. If it is negative, it will move down. Now, whenever we apply multiple transformations to the graph of any parent function, we want to think as if we are simplifying an algebraic expression. And when we simplify algebraic expressions, we have to follow a specific order. Like, remember that multiplication and division will have priority over addition and subtraction. So that tells us that the coefficients a and k that are multiplying respectively the y values of the parent and the x coordinate of the parent will be applied first in the transformations of functions, whereas the coefficients d and c that cause translations horizontally or vertically are applied last. And that's because they are simply additions to the function or to the graph of function. In order to remember the order of transformations, we're going to say that first we have to apply the compressions or expansions that can be caused only by a and k. And for this, we're going to use the acronyms C and E. And next, we will apply the reflections. Now, remember that reflections will come from the sign of a or k becoming negative. So that has priority over addition and subtraction because it's attached to these higher priority coefficients. And lastly, we will apply the translations, and the translations in both horizontal and vertical direction are applied simultaneously normally because they're not easy, they're simpler, easier to use and apply. Now, we're going to take a look at our first example, f of x equals negative x minus 3 power 3 plus 4. The first thing we want to do is identify the parent function. Now, the parent polynomial function we're working with here is f of x equals x to the power of 3. And then we'll look into the coefficients. So, coefficients will be any other numbers besides f of x and x. So what I see in here is this negative sign. This is sitting in front of x cubed in here, so in front of the function, which tells me that that negative sign represents the value of a, which is negative 1. So when a is negative 1, there are no particular stretches happening, but the sign is negative, which tells us that the function is being reflected. And what values of the function are reflected? Well, that's coefficient a. It changes the y values. So the y values are changed to opposite by going to the other side of the x-axis. Therefore, we're going to say that there is a reflection over the x-axis. Next, we're looking at number 3. Number 3 is the number that is being subtracted, in this case, from x. So that means that will represent coefficient d, this very coefficient in here. Think of this negative sign as part of the function itself. And when we're subtracting a positive, that means that the value of d is positive. If it makes it easier for you, think of the parabolas, because that's when we encountered this idea for the first time. So when you had the parabola x minus 2 squared, so when you saw a minus, you said, oh, that's to the right 2 units. Now, with d of 3, we're going to say that the function is undergoing a horizontal translation of 3 units to the right. And lastly, we have coefficient c, which is 4. And we're going to say that a c of 4 will cause a vertical translation of 4 units up. So let's get to the graph now. We're going to start off with the equation of the parent function. And then we'll continue with the equation of y equals negative x to the power of 3. And that's because we're multiplying by negative 1. So we're applying a equals negative 1. And then we'll continue with the graph of y equals negative x minus 3 to the power of 3. And lastly, we'll draw the graph of y equals negative x minus 3 cubed. And we'll add the number 4 to the end of it. So we're going to get started with our parent function y equals x cubed. Now, as you can see in here, I left the y-axis unscaled so that we can set up the scale accordingly. And you remember that the y equals x cubed function will have 0, 0 as one of its points. It's easier to remember. When x equals 1, x to the power of 3, so 1 power 3 is 1. So that will make actually the value of y equal to 1. But let's set up a scale in here. We're going to let two units be represented by 1 square. So we have 2, 4, 6, 8, 10, 12 in here. We can go 14 if you wish. Okay, so we go negative 2, negative 4, negative 6, negative 8, negative 10, and then negative 12 here. So when x equals 1, y is 1, that would be another point. When x equals 2, it means that 2 to the power of 3 will be 8. So x 2, y 8 will be right here. In a similar way, we have x negative 1, y is 1. Remember, it's negative 1, so remember that, again, 1 square is 2 units, so 1 unit will be half a square. And when x equals negative 2, y will be negative 8. Now, we are going to connect these points nicely in a smooth, gentle curve. And as you connect these points, be sure to extend it a little bit beyond the points that you plotted exactly, just to give a better view of the graph and make the graph more presentable, and label the graph by its equation, which in our case will be y equals x to the power of 3. Now, I'm just going to mention this because I encounter it so often, so I see it happen very often that sometimes when drawing polynomial functions, once we reach the point that we know is on the graph, like people will draw the graph a little bit skewed. So remember that the polynomial functions are represented by very smooth curves. They don't just take abrupt corners, and we want to make sure that when we draw the graphs, we keep that in mind. Now, next we're going to draw the graph of negative x cubed. As we mentioned before, now the x cubed values, so the y values, are flipped over the x-axis. So 0, 0 has nowhere to go, but this point here will go to the other side of the y-axis. So I'll mark this point. Y equals 8 will go to the other side of the y-axis. Y equals negative 1 will go to the other side of the x-axis. Did I say y-axis? It's x-axis, of course. So y equals negative 8 will go to the other side of the x-axis. And here go the points for y equals negative x cubed. So here we go again. We'll connect the points and make a nice smooth curve and extend it a little bit and label the graph. Don't forget to label every intermediate step. Next, we'll continue with the horizontal translation. As I mentioned, these are done together, but just for the fun of it, and since it is our first example, I'm going to apply them separately. So 3 units to the right first. Doesn't really matter which one you do first, by the way, so it's the same thing. So remember, we are transforming the red graph. So from the red graph, we're going to the right. So we're going to the right 3. So 1, 2, 3 here. And now we're going here to the right 3. 1, 2, 3 in here. And now to the right 3. 1, 2, 3 in here. Next, we're going to the right 3 here. 1, 2, 3. And to the right 3 for this point. 1, 2, 3, and there we go. We'll connect these points in a nice smooth curve again. And we'll label the graph by its equation. So y equals negative x minus 3 to the power of 3. So lastly, we're going to move it 4 units up. Now we're going to be very careful in here. Remember that 4 units up means that every point is going to move 2 squares, okay? Because 1 square is 2 units again. So we're going to go ahead and move this central point in here 2 units up, 4 units up, or 2 squares. See, it kind of gets you. So again, we're going to have 1, 2 squares, which is 4 units up. We're going to go 1, 2 squares, which is 4 units up. And in a similar way, we have in here 1, 2 squares, or 1, 2 squares, or 4 units up. And lastly, we have 1, 2 squares, which is 4 units up. And here we go. We'll connect the points, nice and smooth and slow. Enjoy the process. Here we go. Here we are, and we have y equals negative x minus 3 cubed plus 4, and you have created in this way a beautiful graph that is also accurate, by the way. So next, we're going to look at another example. You can try this definitely on your own. It's not that difficult. I will continue explaining it in case you want to follow. So we're going to start off with the parent function. So gx, in this case, parent function is x to the power of 4. And then we'll list the coefficients. So I see 0.5 in here in front of x to the power 4, meaning that is multiplying the y values of the function. So a equals 0.5. So that is less than 1. So we're going to say that this will make the graph vertically compressed, and it will get 2 times shorter. And the way you would know it is if you wrote that decimal into a fraction. So you would say 1/2 or 2 times shorter. Now, some people like to say vertical compression by a factor of 2, which makes sense when you think of it this way. Vertical compression by a factor of 2, so compression has been applied, by twice. But some people like to say vertical compression by a factor of 1/2, stating in this way that the y values have become 1/2 of what they used to be. So different ways of saying the same thing, but be very mindful when you use the terminology. Now, last we have -1. This is a number that is being subtracted from the entire function, so that will make the coefficient c, and that will cause a vertical translation of 1 unit down. So let's start with the graph of y equals x to the power of 4. So this is that U-shaped graph that we've drawn in the previous lessons. X equals 0, y equals 0 is the first and easy starting point. When x equals 1, y would be equal to 1. And when x equals 2, remember 2 to the power of 4 will be equal to 16. I don't think we have enough room for 16, but let me check and see how many units we have here. 1, 2, 3, 4, 5, 6, 7. We can't even make it to 8. So what we're going to do is we're going to use these 3 points, and we'll make the assumption that the graph is going to go ahead and increase really, really fast here. And here we go. So we're going to use just these 3 points for the graph of this function. And this will be the graph of gx equals x to the power 4, or the parent function. So next we're going to apply the vertical compression. So 0, 0 won't change, but this point here will have the y value half of what it was. So it was 1, it becomes half. And now the graph will look a little bit wider at the bottom. And I will try to I'll extend it all the way here, just to give us the vision that the graph is indeed shorter in this case. Now, and last transformation would be the, this would be y equals 0.5x4. Let's write it down since we're at it. And then the last transformation is y equals 0.5x to the power of 4, and then minus 1. So we're moving the points 1 unit down. Okay, so they kind of get very, very close to each other in here because the function is, it's kind of a higher power function, that's for sure. And we're going to say that this would be 0.5 x to the 4 minus 1. And this is the graph of the function in example 2. So we'll continue with one more example. So in this question, we are told that there is some polynomial function, and we're asked to determine or to explain how many real zeros or how many x-intercepts would the graph of a function have if we knew the power of the function. So we're going to look at multiple examples in here. Now, this is part of a lesson that we went over. Like, I think it was in lesson either 2 or 3. And what I'm going to do here is try to draw various functions. I'm going to make a bunch of axes, set of axes in here, so that we have enough room to express our thoughts and ideas. So let me just copy more all together. Let's see, maybe we'll need all of them, maybe not. And I'll do the same thing here. Let's see. So what happens if n equals 3? If n equals 3, we can have a graph of a function in the form y equals x to the power of 3, which we are very familiar with. It's going to look like this. This is going to have one x-intercept. It's the simplest third-degree polynomial function we can draw, and we see that there is one x-intercept. Now, we know that graphs of polynomial functions are curves that become more complicated as the degree increases. So, for example, if you are in degree 1 polynomial functions, you have only one straight line, but degree 2, you have not just one, but two lines connected in a smooth curve, either this way or this way. Now, when you go third degree, you can have three lines connected in a smooth curve that can go either this way that I just drew, or it can go the other way around when a is negative. So what we're going to do is try to draw another graph of this polynomial function of degree 3. And this time I have in mind this graph in here. And you see that in this case, we'll see 1, 2, 3 x-intercepts. Now, to make things interesting, I'm going to use this very graph in here, and I am going to try to produce different number of roots. In this case, I'm going to let this be a double root. You should be familiar with this concept. If not, you can review the lesson. I think it's lesson 3 for sure. And you see that in this case, we will have the graph will make 1 or 2 x-intercepts. So you see that the graph can have 1, it can have 3 x-intercepts, it can have 2 x-intercepts. And now we're thinking, is it possible for this graph to have no x-intercepts at all? Now, due to the end behaviors of all degree polynomial functions, where the y values are increasing in one end and decreasing in the other, so it can go this way or the other way around. It's still increasing in one end and decreasing in the other. The y values will have some negative and positive values. So the y can be positive or it can be negative. And we know that polynomial functions are have their domains any real number x, their continuous function. So when a quantity is changing from positive to negative or vice versa, it has to pass through its zero. So that's the reason why the polynomial functions of degree 3 always need to have an x-intercept, at least. So this is the least number of x-intercepts, least one x-intercept, and you can see that it can also have more than one, so it can have 2 and it can have 3. Now, you want to think, can it have more than 3? As a matter of fact, more than 3 is not possible because of the graph of a function that can have at most only these 3 lines, so that can cut the x-axis. So we're going to say that the most number of x-intercepts it can have is 3 of them. And I think that we're now ready to move on to the graph of a polynomial function with degree 4 and see the number of x-intercepts available there. I'm going to start off with a basic polynomial of degree 4, x to the power of 4. As you can see, there is one x-intercept in here. And if we were to move this graph a little bit higher, you see that this graph can escape the x-axis, make no connections, so no intersections, and the graph can have also no x-intercepts. So one x-intercept or no x-intercept. So I'm just going to draw the graph here, a different one, doesn't matter. So it can have one, it can have none. Now, just like we drew the cubic functions with these curvy lines, we can also do these for the, we do the same thing for the fourth degree polynomial function. So here we go again. We have 1 line, 2 lines, 3 lines, 4 lines, connected in a smooth curve always. So as you can see here, we have 1, 2, 3, 4 x-intercepts. Now I'm going to grab this very graph again. I'm going to make a copy of it actually, and I'm going to use the same graph to make more or different number of x-intercepts. So if I place it in here, you see that you have 1, 2, 3 x-intercepts. So here we go. So we have 4 in here. We have 3 in here. In what other ways can we draw the graph of a fourth degree polynomial function? So, well, it doesn't really matter if it opens up or down, so intercepts will look the same way. So let's not focus on that for now. So another way we can draw the graph of a polynomial function is by first making a third order root or third order x-intercept. So here are 3 powers, and now I'm going to make a turn. And you can see that in this case we have 2 x-intercepts. Another way the graph can make 2 x-intercepts is by, when you have, let's say, for example, a W shape, and the graph is touching just at these 2 points. Or when this W shape can be moved down like this. That's another possibility, 2 x-intercepts. But what I am noticing so far is that the graph can have no x-intercepts. It can have 1. It can have 2 x-intercepts. It can have 3 x-intercepts. Or you can have 4 x-intercepts. So we're going to say that the least number of x-intercepts for this graph for degree 4 polynomial functions will be none. And the most will be equal to 4. So that will equal the degree of the function. And as we've mentioned in the past, the most number of x-intercepts any polynomial function can make is equal to the degree. And for the least number of x-intercepts, the degree matters because all degree functions will have to make at least 1 x-intercept, whereas even degree polynomial functions can escape the x-axis without making any contact at all. This is the end of the practice questions with multiple transformations, applications of multiple transformations in polynomial functions. I hope you enjoyed the lesson. I hope that you found the instructions useful, and I thank you for learning with me. Bye for now.